So now the first part should be about time-dependent problems. So we have a few lectures on time-dependent problems, time-dependent scalar problems, Navier-Stokes, wave equation, and then going towards nonlinear problems at the end of this section. Okay, let me start with a very simple problem, parabolic model problem. So we have convection diffusion equation, time-dependent on the domain omega, and we have a given wind velocity b. Okay, so the usual stuff, loading some libraries, setting up geometry, so the unit square with the labels that you all know, bottom, left, right, top. Nothing fancy about this. And now we want to, after also seeing some bilinear forms and matrices that we're all familiar with right now, we want to do some time stepping. So I already define a time and some time step. Here dt is my time step. Okay, so the velocity field in the example that I want to consider is the following one. So this guy, it's a divergence-free velocity field, and yeah, it's this vortex essentially on the unit square. All right. Now what we want to do is we want to consider convection diffusion equation with that given and time-independent velocity field. Okay. Yeah, you all know how to set up bilinear forms and the corresponding sparse matrices. So what we do now is we do the corresponding part for the diffusion part with a diffusion coefficient 0.01 here. For the convection part, so it's B gradient U times V. And then we have a mass matrix here. And you see already something that we, I think, haven't discussed yet, but most of you might know already. So you can prescribe if a bilinear form is symmetric or not. That means if during storage of your matrix entries you exploit that you have a symmetry or not. So obviously for the A bilinear form you cannot do this because the problem is not symmetric. For the M bilinear form you could do that. However, we don't do this because we want to have the sparsity pattern of both matrices available, as we will see in a minute, in order to make linear combinations of matrices. So keep that in mind. So the symmetric flag is set to false here. Okay, so we want to solve a very simple problem with a very simple discretization. So what we want to do is we want to apply an implicit Euler method. So this is why we also need the mass matrix. So we have to solve the following problem. So we have mass matrix plus delta t diffusion matrix for the new time step and then corresponding right-hand side. We also write this in an incremental form. So we have this M star matrix times the incremental that we search for, which kind of indirectly defines our new time step value, is equal to the corresponding right-hand side. So what the first news aspect should be now is we don't want to assemble the M star as a bilinear form with an assembling afterwards, but we rather want to assemble M and A, what we did on the last slide, and we want to form a linear combination of those matrices. And kind of the thing where you have to be careful, that I also already addressed this, you have to make sure that the sparsity patterns of those matrices are the same, so that what we'll do in a minute also works as it should. So this is why both symmetric flags were set to 0. Okay, what we now do is we create a new sparse matrix, which should have the same layout as the M mat matrix. So this we can do with a create matrix, similar to what we saw with create a vector. So this gives us a sparse matrix with the same layout as the corresponding underlying matrix before. Okay, so if we do this, so what we see then is that the number of non-zero entries of all those three matrices, so M, A, and this new M star, is all the same. And if you take a look at the entries, okay, you could check that this is the same memory layout as before. Okay, so what you can do with a sparse matrix is you can actually access the entries of the matrix by calling this S vector, which returns you a vector, obviously, and you will see this vector has as many entries as you have non-zero entries. Okay, so you can also print the entries, and you can check that these are the same that we saw before on the slide. The corresponding first entries are 0.005 something, and this is then the first entry also of this vector. Okay, and this is what we use now to form this M star matrix by just using that the entries, so the values in the sparse matrix, that we can just linear combine them. Because we have the same memory layout, we will get the corresponding correct matrix. So what we get out of this operation here is the same as if you would assemble a corresponding bilinear form with the corresponding terms inside. Okay, then we invert this already to prepare the ellipsoid Euler step. Okay, so we set up some right-hand side to make the problem a little more interesting. So this is the kind of two Gauss peaks that you have. So we have a blob at the left positive and a blob on the right negative. So sources and sinks that we want to incorporate in the problem. Okay. Yeah. So, okay, we set up the matrix, the solution vector. We create a temporary vector, as I said, with the create vector part, and consider already the time loop. So this is now the time loop. Also nothing fancy if you compare this to the previous tutorials. So we just do the right-hand side for the incremental form. So we have A times UN times delta T with a minus, and then the corresponding right-hand side. We do the inversion of the M star matrix, and we add this up in the time stepping scheme. Okay, so if we execute this, this is kind of the evolution for a few time steps, where you can see kind of how, due to the boundary conditions and the source that we prescribed, that there's some nice pictures essentially coming from those initial values. Okay, so as we already learned we can also work with base matrices and iterative solvers. So you could also think about not really creating a sparse matrix with new storage and new values for this M star matrix, but just defining essentially the matrix through its operation. So here we have M star alt for alternative, which just defines the matrix as the linear combination of the operators that you have. So you can apply matrix vector multiplication now, but you cannot call the inverse, so the sparse inverse operation on that. Similarly, you could try doing a corresponding Jacobi preconditioner just by setting up this as a linear combination of the corresponding Jacobi preconditioners of the individual matrices. And then you could solve this iteratively. I introduced a star here. Okay, and then the result, for example, for this preconditioned matrix is just the base matrix, so there's no storage involved in this matrix here. You could solve the same problem again. It's much slower now because, yeah, the iterative solver is not the best to do, just a Jacobi preconditioner, obviously, on the problem, but in principle, you can do this. You can circumvent setting up a new matrix. Okay, so this was a very simple starting point to solving time-dependent problems, and many components you already saw somewhere else. There are a few other details that I will not go into, so there's some supplementary material for you later on if you're interested. So how to kind of change the problem to have a time-dependent right-hand side, how to involve time-dependent boundary data, how to do Hohen-Kutter schemes, so higher order time integration, or how to do VTK output for making videos or kind of pictures for post-processing. Okay,